Good evening. This is our presentation for the paper entitled Time Series Data Augmentation and Dropout Roles in the Deep Learning Applied to Fault Detection. And the authors are Enol Garcia, Jose Villar, and Enrique Decada, all of us from the University of Oviedo. The table of contents include an introduction to fault detection, the data augmentation and the dropout that we propose in deep learning, the obtained results using the UMA fault dataset, and the new developments that we are working on. Well, fault detection is a main problem for elderly people, and once a person falls, there is an increase in the fears and self-consciousness of the fragility, so they started being quieter and they're not moving, they reduce their activity, and all of that is a problem because that makes that decreases their health, and by the time the casualties increases. There have been a lot of studies of how to solve fault detection using different devices, such as some personal assistance detectors, or images, or video analysis, sound, etc. Also, there has been wearable sensors that the person needs to use, such as smartwatches or some specific device placed on the wrist. Of course, it will depend on the type of faults or the type of individuals that you are focusing on to choose the best sensory system. For if you are thinking on patients such as Parkinson, there could be interesting then to have a sensor on the waist. But if you are thinking on people living autonomous living, then we will need something like a smartwatch or something that does not interrupt or disrupt their everyday life. So we have focused on using a smartwatch on a wrist, and in this context, deep learning has been applied. There are some studies using convolutional networks, such as the one published by Casirari, that is the base work from this study. The main problem of that is that in all of the papers up to our knowledge, the datasets that are used are basically public fault detection datasets that includes instances with multivariate time series for human activities or for staged faults. And the staged faults, we can see it here in the right part of the image of the slide. We have the evolution of the accelerometry sensors on a wrist for one staged fall, and we can see here that there is no activity before or after the fall. After a fall is a normal situation. You fall, you might feel dizzy and do not move, but before there should be a cause of your fall. Of course, you can have a faint, but normally you are moving, you are walking, running, etc. So there should be something here. And what we propose in this study is that, hey, just introducing a simple data augmentation, we are going to improve the performance of the system. And that was what we propose here. We introduce a data augmentation and see if the obtained results are enriched. So first of all, we use the same model proposed in Casirari. You can see the model there on the top part of at the right of the slide. You have a convolutional layer with a normalization layer, then the ReLU and the max pooling, and then you will have that replied several times with 16, 32, 64 and 128 filters, and then we have a dense softmax layer. And the output of that is just a true or false, and the input is a time series. To that proposal of Casillari, we introduced the dropout that they didn't, and dropout with 50%, and the data augmentation. So the data augmentation that we propose is just so simple as this, just shifting to a right or shifting to a left, the fault detection, the fault instance or stage fault instance, and that's all. Of course, we have different possibilities. We could have rotated it, or we could have done some scaling, but in this case we just shift it and try to learn the models and see if they goes better or not. And these are the results that we have for the UMA-FOL. The UMA-FOL is a data set published by Casillari et al. At the University of Malaga, and it has data from 17 participants from different ages performing human activities such as walking, running, hopping, sitting, etc. And also stage falls. The stage falls are 4 types of falls. Are a lateral fall to the right or to the left, backwards and forward falls. There is no one of the problems of this data set is that they do not have the same number of repetitions for all of the participants, but in any case there is a if I remember well, we have 207 stage falls out of 530 time series. So it's okay, it's a valid data set. And what we can see here is the results of accuracy, specificity, sensitivity and kappa without the data augmentation and dropout, with the data augmentation, and with data augmentation and the dropout. As you can see, just introducing such a simple data augmentation makes models to perform to better detect the anomalies, or actually what they learn is to discriminate better among non-fall and fall time series. And once we introduce the dropout, then we obtain a much better performance, as you can see on the right of the slide. Well, that was not surprising at all. So we are now working on more things. First of all, we have introduced a more complex data augmentation. What we have is that in mind is to and we have already implemented that. You can see here is the output of our data augmentation, that is mixing human activities signals and stage-of-fall signals. So we use the time description of Capricci for the fall detection, for the fall stage fall, to identify the point at which the fall starts, and then we mix it with time series from an activity, human activity of the same participant, and we made a merging of the two time series. So the output is one part with human activity, and then the stage fall and the quiet period afterwards, after a fall. We also introduced shifting and scaling to our data augmentation, and we are pending to introduce the rotating of the time series. So It doesn't matter how you have your wrist, that we will also consider that case. And we have considered different models. The ones that you have here on the right is a ResNet, then a Musin model, and the show model using the two letters use a long short-term memory. We are now coping with that. We are now obtaining the results for these three models, but we are working on it. And this is all. Thank you so much for your attention.